All right, hello everyone. Welcome to the Denver Museum of Nature and Sciences Facebook Live event today. My name is Kachun Yu, and I am an astronomer, the curator of space science at the Denver Museum. And I've done a lot of work with our planetarium, and today we will be showcasing our planetarium software that we use for live events in the dome. But since we're not doing that, you get to see it here. So what I want to talk to you today about is about really how big the universe is. It's awesomely big, and hopefully you'll get a sense of that after today's talk. And you should be seeing the International Space Station orbiting behind me. And it orbits about 240, 250 miles above the surface of the Earth. And I'm actually controlling the software, as you see. And if you were an astronaut on board the International Space Station, this is in fact how fast it would orbit around the Earth. You would actually see the Earth slowly stream by underneath you because the ISS is moving about 17,000 miles per hour. That's how fast it has to be orbiting around the Earth in order not to fall towards the Earth. Instead, it's falling around the Earth. Now, it orbits at about 240, as I said, up to 240 miles above the surface of the Earth. And if you think about that, that's not very far at all. 240 miles is about the distance between Denver and Grand Junction. And so if you've ever taken a road trip along I-70 towards the west to Grand Junction, that typically takes about 3.5 to 4 hours. And so you can imagine if your car could magically drive straight up into the air, you would actually get up to the spot where the ISS is orbiting in only a few hours. So space isn't that far, and where we have astronauts living in space is not very far from the Earth. So if we fly out from the ISS, you can see it disappearing, and we're actually seeing Colorado now. Just over my right shoulder, you'll see the Front Range, but I'm gonna pull us out and fly away from the Earth. And so since we don't see the International Space Station anymore, you can get a sense of how close it hugs the Earth and its orbit. And as we fly away from the Earth, or blue marble floating in space, we now start to see the orbit of the moon. And so oftentimes, if you look at pictures in a book or on the internet, you get the sense that the moon and the Earth are really close together, but they are actually separated by about 250,000 miles. And so it took astronauts in the Apollo era about 3 days to travel to the moon. And another way that you can think about distances, since we have to deal with such big distances in space, is light travel times. So how long it takes a radio signal or light traveling at the speed of light to get anywhere. And so if you were looking at a friend from across the room, light travels about 1/1000th of a second every foot. So someone who's socially distanced 6 feet away, light has taken 6 billionths of a second to travel from that person to you in order for you to see that person. So you're actually looking at people at least 6 billionths of a second in the past. If you're looking at the moon is just over 1 light second away. So you're seeing the moon 1 second, a second and a quarter or so in the past. And as we keep zooming out, now we see the orbit of the Earth. And now we're seeing the orbits of the other planets. There's Mercury, Venus, Earth, and Mars. And the distance between the Earth and the sun is about 8.5 light minutes. So now we're talking about distances that are so vast that even light traveling at the speed of light takes roughly about the amount of time that between commercial breaks in a sitcom. So that's about 8.5 minutes. And so when you look at the sun out in the sky, it's kind of overcast in Colorado right now, so I can't really see the sun, but you're seeing it 8.5 minutes in the past. And so if the sun was to blink out of existence, you won't actually be able to see it for 8.5 minutes. And as we keep traveling further and further out, we're going to vaster distances. The orbit of Neptune is about 4 light hours from the sun. So that's how long it takes light to travel out to Neptune from the sun. And then what I'm going to do now is to turn on some trajectories for the Pioneer spacecraft. These are spacecraft that were launched in the early 1970s, and these pair are only two of the five spacecraft that we've launched that will escape our solar system completely. And here you can see one of the trajectories, and they show the dates of where the spacecraft are in time. So 2020 is visible. So we just slipped into 2021. And in parentheses, that number tells you the number of light hours. So how long it takes radio signals traveling at the speed of light to get back to us on Earth. So for this spacecraft, it's 14 light hours. And if we come all the way to 2050 for Pioneer 11, you can see that it takes about 24 light hours. And these spacecraft will continue traveling. They're not going to stop in the year 2050, but 2050 is roughly about 70 years after they were launched. So basically, some of our fastest spacecraft traveling ever launched by humans, after about a human lifetime, after about 70 years, they will have only gone about 24 light hours or 1 light day. And that's still extremely small compared to how big the universe is. So I'm going to keep zooming us out. And we'll see the Oort cloud, which is a giant cloud of comets. And this is roughly about 1 light year and a half. And so now we're dealing with distances to the stars, where distances are measured in light travel times of years instead of hours or days. And I'm going to turn on the constellation lines. And so the constellations are simply just the patterns that we've associated with the stars. And we often have stories that we tell with the constellations, but as we zoom out, you'll start seeing the constellations themselves start to distort. And that's just because the stars are not located all evenly distance from us. They are actually spread out in 3-dimensional space. And so the constellation lines are now starting to distort. And the visible stars, which make up the constellations, they're no more than 1,000 or 2,000 light years away. And so as we keep zooming out, you'll see more stars. And now we are out at the scale of our Milky Way galaxy. So we've never sent spacecraft out here, but we do have pretty good ideas of what our galaxy is like. It's a giant barred spiral galaxy, about 100,000 light years across. And so a beam of light starting at one edge of the galaxy would take 100,000 years to reach the other edge. And as we keep zooming out, we're not going to see stars anymore. We're going to see other galaxies. And so each of those dots, those colorful dots, is associated with another galaxy. The colors represent different groupings or gravitational clusters of galaxies. And as we keep pulling out, you'll see the large scale structure of the universe. And now we're looking at tens and even hundreds of millions of light years away. And finally, we're not going to go out too far, but I will turn on the cosmic microwave background, which is the furthest that we can observe in the universe. And this is limited by the light travel time to the edge of the Big Bang. So we know that the universe had a beginning about 13.7 billion years ago, and you can't see any further than 13.7 billion years. And so what we're seeing is the afterglow of the Big Bang, that was light that was emitted soon after the Big Bang. And it's the furthest limit that we can see. And so with that, I'm going to head us back home towards our solar system and planet Earth and memory. I'll be happy to take questions from the audience. And as we zoom back, we'll continue to fly and navigate the simulation.
Gotta fly on back to Earth. And yes, while we fly, how about we look at some of these questions? Hi, everybody. My name is Memory. I work in the marketing department here at the museum, and I am just here as always to share your questions with our presenter. I am monitoring Facebook and YouTube. So if you're watching on any of those, just drop that comment and we will get those questions to Kachun. And we do have a few. So how about we get started with those? We have a few on Facebook. Here we go. Carla asks, Are there signs of water in Mars? What about the moon? That's a good question.
Yeah. What about Mars? So I'm gonna target Mars and see if we can fly anywhere in the simulation. That's a great question. Let's fly on down to Mars. So we had flown away from the Earth, and everyone probably remembers what the Earth looks like. It's blue of the oceans, the white of the clouds, and there's green on the land, and that's from the vegetation. And all that are signs of water. But when you look at Mars, you can see that there's no hint of water at all. There's actually some water ice in the polar caps, as well as carbon dioxide ice. But we think Mars probably does have some water ice locked underneath its surface. The surface is otherwise very dry. And if we zoom up even closer, you'll see that there are features that look like they were carved by running water, by rivers that ran on Mars 3 to 4 billion years ago. So here's one now that almost looks like a kind of a sinuous river. And but since then, Mars has dried up and it's lost most of its water to space. So we think Mars was warmer and wetter in the past, but there's no water now.
Interesting, interesting. Oh, we have a question from YouTube. Lauren asks, hello, how much closer to the sun is Mars than Earth? And how big is our galaxy? And this is a question from her 3-year-old. Thank you so much for asking that. All right.
All right, so let's look at our solar system again. And you can actually see Mars is actually further away from the Earth. So Mars is the red orbit, and Earth is kind of that greenish orbit. And Mars is actually about 50% further away from the sun than the Earth is. And so Mars does get less energy from the sun, less light and heat. That partly accounts for why Mars is a lot colder. So a warm day on Mars is like Antarctica here on Earth. And as far as how big our galaxy is, that collection of stars that we saw earlier that make up our spiral galaxy, the Milky Way, it's about 100,000 light years across. So it would take a beam of light 100,000 years to traverse the galaxy, to travel it from one edge to the other.
Awesome. All right, we're getting in more questions on Facebook. We have a question from our top fan, Mina, who asks, do all stars have their own Oort cloud? I hope I'm saying that right.
Yeah.
O-R-T. Are Oort clouds all 1 light year in radius, or would bigger stars have bigger Oort clouds?
That's a really good question. And actually, we don't actually know the answer to that. So as we zoom out, here we're seeing the Oort cloud again, which is a hypothetical cloud of comets. And by hypothetical, I mean, people think this cloud of comets exist around our sun, but we've never actually detected comets out here. We've never actually observed them with telescopes. We can only guess that they must be there just based on where comets appear to come from when they fall in towards the sun. And so we think this Oort cloud of comets might have been created when comets closer to the sun got flung out to these distances by Jupiter's gravity. And so if another sun, another star had similar planets, really large planets, and they had similar groups of comets closer in that gravitationally interacted with the large planets, those other stars might have similar Oort clouds. But right now, we really don't know, just because it's difficult to observe our Oort cloud. We haven't been able to do it or observe the comets in our Oort cloud. And so we don't quite have observations of other Oort clouds just yet.
Interesting. All right, and back to YouTube, we have another question from Scott, who asks, if our best tech from 50 years ago can only get a light day away, do we have any missions based on current tech which are intended to go much further and much faster?
So that's a really great question, and the answer is unfortunately no. And it has to do with how, all of our spacecraft missions so far that we've sent out have been used to observe or to explore the planets. And so in addition to the Pioneer missions, there are also the 2 Voyager spacecraft. And so I've turned on the trajectory lines for all 4 of those. They were used to explore the outer planets, Jupiter, Saturn, and then also Neptune and Uranus for Voyager 2. And we've also sent a spacecraft out to explore Pluto, which, and I'm trying to figure out if I can turn on Pluto's orbit. But that was the New Horizons spacecraft, which flew by Pluto about 5 years ago. And so those spacecraft were launched, and they only have enough fuel to do course corrections. And so most of their speed was from the big rocket that launched them, and then any gravitational assist, meaning they were able to slingshot around bigger planets to get speed. So they don't have any or enough fuel for them to continue increasing their speed. And so that's why all of our spacecraft have been really pokey. They've been pretty slow. And so right now, we really don't have the technology to send things that go, that continue to accelerate, that go faster and faster, and to have us get to the nearest star within a human lifetime.
Interesting, interesting. Thank you for that question, Scott. Really good question. We have another one on Facebook from Barb who asks, what is the coldest planet?
Well, Barb, I guess the question I can return back to you is, what makes things cold or warm? And since we don't have that much time, I'll just give you 2 seconds to think about it. But the answer is it's the sun. And so the closer, to kind of to first order, the closer something is to our sun, the warmer it is. And as you get further and further out, the colder it is. Now, there are some things that can make planets warmer. One of them is an atmosphere. And so if an atmosphere has heat trapping gases like carbon dioxide, they can make the planet warmer than if the planet didn't have an atmosphere. And so our Earth is actually habitable because of the small amount of heat trapping gases in our atmosphere, carbon dioxide as well as water vapor and other gases. But of course, if we have too much of it or pump too much of it into our atmosphere, it makes our planet even warmer. Great question, Barb.
Great question. Yeah, let's see if we can get to these last few before we end. We have another question on Facebook from Coralie from Archer, who is 5 years old. Thank you both for watching. And Archer asks, why is the sand on Mars so red?
Why is the sand on Mars so red? So let's, I'll just jump to Mars just to speed us up. And so Mars is known as the red planet. You can, if you look at Mars in the sky, you actually see that it looks slightly reddish compared to other things in the sky. And in the simulation, you can see that Mars kind of has a dirty orange or rusty kind of look to it. And that color is due to rust, iron oxide. And so if you have iron ore here on Earth, it combines with oxygen in the air to create rust, which is brownish in color. And so it turns out that the sand on Mars, the soil on Mars, does contain a lot of iron, and it has combined with whatever oxygen is available. And so the color on Mars is due to the same sort of stuff that you find here on Earth, rust. But there's not that much oxygen on Mars, or actually pretty much all of it has been combined. And so there's pretty much no oxygen in the atmosphere, but all of it is actually on the surface that we can see.
Awesome, awesome. And another question about Mars from Jeff and his son Jacob, who want to know, what's the surface temperature of Mars?
I'm trying to remember what the surface temperature is. Most of the time it is below freezing, and of course Mars does have seasons similar to what you have on the Earth. And so during the summer it can get warmer, And if I remember right, I'm not a Mars scientist, so I'm trying to remember here. But sometimes, Mars can get into temperatures that humans could survive in. So, temperatures in the 20s, 30s, and maybe even the hottest temperatures could go above freezing and maybe to the 40s for Fahrenheit. But for the most part, Mars is a very cold world. And part of that is because it actually has a very thin atmosphere. So even though it's only 50% further from the sun, the very thin atmosphere, meaning very little heat trapping gases, means that it's actually much colder than it would be if it had an atmosphere as thick as the Earth's.
Awesome. Awesome. And how about we take a few more questions as we round out on time? We have another one from Mary on Facebook who asks, what are the relative speeds of Jupiter and Saturn? I've watched them over the past several months and saw them get closer than they are now, separating. They seem to be moving really fast to us here on Earth. Thanks. Thanks for watching, Mary.
Yeah, so let's see. I'm going to jump to our present day. And because we just, for many of you, you probably heard in the news recently that we had this conjunction between Saturn and Jupiter. And what that means is that they appear to be in the same direction in the sky. And so this is, the conjunction happened or the closest that they appeared happened on December 21st. So just a few weeks ago. And this is what they look like current day. And you can see that they're not quite aligned, but compared to where they are on the, so here is the Earth. The Earth is over here. And I'm going to go ahead and turn off Mars I'll turn off Mercury, Venus, and Mars just so they won't confuse things. And I'll turn off some of the other, whoops, I got to leave on Jupiter. And so you can see from where we are on the Earth over here, Jupiter and Saturn do appear to be in a line. And I don't know, miles per hour, how quickly Saturn and Jupiter are orbiting, but they're typically on the order of many thousands of miles per hour, just because space is so big. But if we were to turn on time, and I'm going to move us through time at about 1 day per second, and you can see that, well, Jupiter and Saturn don't really appear to be moving at all. They move really slowly, at least at this distance. If we move maybe 3 weeks per second, now you can see Jupiter really moving along. And you can also see the Earth really moving along because it takes the Earth about, well, 365 days, 1 year to go around. And so everything in the solar system are moving. They're in orbit around the sun. And every 20 years ago or so, Jupiter and Saturn do catch up to one another since they are also orbiting the sun. But this conjunction was really noticeable just because of where they were in the sky. And so that's why we heard about it. Great question.
Yeah. Okay. And how about we take these last two questions and then we'll wrap it up. But if you have any more questions or you look at this video later on and you have more questions, just drop those questions right in the comments. I'm happy to email those to Kachun and we can get that answered for you. So for our last two, we'll take this last one from Scott, who asks, back on YouTube, would you mind providing a basic explanation of the string theory and how it differs from the mainstream?
Okay, well, I'm not sure I can do justice to string theory in just a couple minutes.
Yeah.
But that's a great question, Scott. But our universe seems to consist of a bunch of particles, like the particles that make up our bodies, electrons, neutrons, protons, as well as forces like the electromagnetic force, electrical force and magnetic force, as well as gravity. And scientists for the last 100 years, if not longer, have been trying to make sense of all the different particles, subatomic particles, quarks, and that make up protons and neutrons, along with the different forces. And they've been struggling to do that, trying to come up with a theory that explains everything. And so string theory is just one of the those options, those ideas that physicists have come up with to explain our universe. And right now, we actually don't know whether string theory is correct or not, because you know, scientists can come up with theories, but they also need observations to try and confirm whether a theory is correct or not, or a hypothesis is correct or not. And so right now, we don't have any observations to say whether string theory is actually correct. And so scientists will continue to work on string theory along with other theories to explain the universe. So that's my hopefully 2-minute take on string theory.
Oh, the string theory. Awesome. And let's end with this question from Carla, who, I mean, this question is kind of making me think, and I'm really anxious to hear what you have to say about it. But she asked, space is always expanding. Is that a fact or theory?
So the expansion to space is definitely a fact. We discovered that the universe is expanding. And by the universe, we mean the universe at the scale of galaxies. So at smaller scales, say in our solar system, or even inside our Milky Way galaxy, nothing is expanding. And that's just because gravity is holding our solar system together. So the planets will continue to orbit around the sun. But at larger scales, gravity is weak enough between galaxies that the clusters of galaxies will be bound together by gravity. But at larger scales, the universe is expanding, and we have lots of observational evidence to show that. And if you run the movie of the universe backwards, you see instead of the universe expanding, it's collapsing. And so we know that's how we know that the universe started in the Big Bang 13.7 billion years ago. But we do have really, really good evidence that the universe is expanding, and will continue to expand far into the future.
A lot to think about with that. We'll end on that point. Thank you everybody for joining our first Science Division Live of the year. We will be back next Thursday with some more awesome science, and we hope to see you then. Thank you.
Yeah, thanks everyone for all of your great questions.